Well, hello, my lovely chemistry students. And you know it's going to be a great day or night, as it is right now, today, because you get to learn more about chemistry. So in this lesson, we are starting our redox unit, and we're going to start off by talking about oxidation states and how they are relevant in redox reactions, as well as how to balance redox reactions. And then we're going to be moving into how these balanced redox reactions can help us whenever we are doing redox titrations. So we've already talked about titrations and how it's used to solve for the concentration of an unknown solution. So specifically, a redox titration is determining the unknown concentration of a solution through a redox reaction. So as we start off with, we have to define what oxidation and reduction are, because a redox reaction stands for reduction and oxidation, aka redox. So oxidation used to refer to the addition of oxygen to a compound. So if oxygen was added to something, they'd say that is oxidized. However, that's more of a limited way to describe oxidation. Additionally, they used to say reduction was the addition of hydrogen to a compound. And again, that is a very limited view because not all oxidation reactions result in the addition of oxygen, and not all reduction reactions result in the addition of hydrogen. So now, whenever we define oxidation reduction, we talk about it in terms of electron movement. So oxidation is whenever a substance loses electrons, and reduction is whenever a substance gains electrons. And you can remember this through the mnemonic Leo the lion says grr, Leo and GER. Leo stands for loss of electrons is oxidation, and GER stands for gain of electrons is reduction. So that's how you can kind of remember that when something loses electrons, they're oxidized, and when they gain electrons, they are reduced. And the way to determine if a redox reaction is taking place is through their use of oxidation numbers. Now, previously we have used oxidation numbers when we were trying to identify how to write the formulas of ionic compounds. For example, we know that the formula for magnesium chloride is MgCl2 because the charge of chlorine tends to be -1 whenever it turns into chloride, because it is in group 17, and magnesium tends to have a charge of +2 when it forms an ion because it is in group 2, so it likes to lose 2 valence electrons, whereas chloride likes to gain 1 valence electron. So there needs to be 2 chlorides to balance out the magnesium, MgCl2. We use oxidation states as hypothetical charges. If all of the atoms in a certain compound were ions. So not all of these compounds will necessarily be ionic compounds. Some can be covalent compounds, but that's just because these oxidation states are used as a tool to track electron movements. So they are hypothetical, they are not real. Like, these are not actual ions, they're just a way to track electron movement. So for example, if you look at the combustion of, I think this is ethine, C2H2, yeah, that's ethine right here. You can assign charges to all of the substances in here, assuming they would form ions. So because hydrogen is in group 1, it tends to form a +1 ion. And so if there are 2 of them in ethine, then that would give you a total +2 charge. Now, if there are 2 carbons, that means each carbon would have to have a -1 charge in order to balance out the 2 hydrogens. And then oxygen, it is diatomic, so anything in their standard states, such as diatomic gases or any type of solid, is going to have an oxidation state of 0 because they are uncharged. Doing the same thing with carbon dioxide, oxygen would have a -2 charge because it is in group 16, therefore it tends to gain 2 valence electrons. If there are 2 of them in CO2, that would make a total charge of -4. So therefore the carbon bound to it would have to be a +4 oxidation state to balance this out. Again, if it were an ionic compound, which it is not, but again, this is just a tool we use to track electron movement. And then for water, we have a -2 for oxygen, a +1 for hydrogen. So we can see what oxidation numbers changed from reactants to products. Well, I can see that carbon went from a -1 over here in the reactant side to a +4 in the product side. So if you are getting more positive, that indicates electrons were lost, and therefore this ethine was oxidized. Looking at oxygen, you can see it goes from an oxidation state of 0 to -2 in both carbon dioxide and water. So because that oxygen is getting more negative, then it is gaining electrons. So the oxygen is reduced and the ethine is oxidized. So every element within that compound has an oxidation state. And again, you look at where those oxidation states change in order to see if something is oxidized or reduced. If the oxidation state increases or becomes more positive, it indicates a loss of electrons and therefore oxidation. And if you see the oxidation state decreasing, that means more electrons are being gained and therefore reduction. And sometimes you will hear the term oxidation number instead of oxidation state. However, according to IUPAC, oxidation numbers are the Roman numerals used with transition metals whenever you are naming ionic compounds that have transition metals, like iron 2 chloride, FeCl2, that indicates an oxidation number of 2 for the iron. When you're talking about just tracking electron movement, you call them oxidation states. So oxidation numbers are real, I say that in quotations, because it tells you what the charge of that metal will be in an ionic compound. So it's kind of a nuance, but just know oxidation state is the correct term to use in redox reactions. So there are certain rules for assigning oxidation states to elements. First off, I talked about how any element that is in its natural state or uncombined, the oxidation state will be 0. So, pure solids or diatomic elements. The oxidation state of a monoatomic ion is going to equal the charge on that ion. For example, if a reaction involves magnesium with a 2+ charge, it's already an ion, then it's going to have the same oxidation state as the charge on the ion. Another rule is that the more electronegative element in a binary compound, which means a compound that only contains 2 different elements, is assigned the number equal to the charge it would have if it were an ion. For example, a binary a binary compound such as sodium chloride, NaCl, you would look at the more electronegative element there, which is chlorine, and assign that the oxidation number it would have if it were an ion, which of course sodium chloride is an ion, but so it would be -1, whereas the sodium would be +1. You can look at hydrogen fluoride or hydrofluoric acid. So hydrogen fluoride is a covalent compound because it has 2 nonmetals, right? So in that case, it's not going to form an ionic compound, but you're going to treat it like that and put the fluorine, or the fluoride as a -1 oxidation state because it's more electronegative than hydrogen, which then would have a +1. Oxygen is always going to have a -2 oxidation state unless it's combined with fluorine, in which case it could be positive, or it's in a peroxide, such as hydrogen peroxide or sodium peroxide. And in this case, the oxygen is going to have a -1 charge because hydrogen always has to be +1 and group 1 elements are always +1. So if that sodium or that hydrogen is +1, that means the oxygen has to be -1 to have a total oxidation state of 0 for the compound. So again, hydrogen is always going to be +1 unless, there's always a but, right? Unless it is combined with a metal, in which case it is -1. So sometimes you can have a metal hydride, such as NaH, that is sodium hydride. So because that sodium has to be +1, in that case, the hydrogen will take on a -1 oxidation state, but that's pretty rare. It's only in hydrides. So I talked to you about group 1 and group 2 elements have their oxidation states of +1 and +2 respectively, and aluminum will always have a +3 oxidation state. I already mentioned that the sum of all oxidation states in a neutral compound is going to be 0, and the sum of the oxidation states in a polyatomic ion is going to equal the charge on that ion. For example, things like carbonate or nitrate, those are charged covalent compounds, or aka polyatomic ions. So when you add up the oxidation states of whatever's in that polyatomic ion, it has to equal the charge on that ion. So this is some important rules to know. They're kind of what I just talked about, but in a table format, if that helps you out. So here's an example. We have a lead lead 4 chloride here. So the oxidation state, that's what OS is, of chloride is going to be -1 because it's in group 17, and there are 4 of them, which means lead has to have a +4 charge in order to balance out this compound because it is a neutral compound, it's not a polyatomic ion. So in this case, the oxidation state of lead is +4, and the oxidation state actually is the oxidation number because this actually is a ionic compound that has a transition metal in it. You can look at a charged compound like carbonate. So you can see that oxygen would have an oxidation state of -2 because it's not bound in a peroxide or to fluorine. So it's going to be -2. That makes an overall charge of -6 because there's 3 oxygens. However, carbonate overall has a -2 charge. So you might want to say carbon is +6 to balance out the oxygens, but it's not because we have to have an overall charge of -2. So in this case, the carbon has an oxidation state of +4 in order to give that total overall charge of -2. And again, like I said, these oxidation states are just tools. So dichlorine trioxide is not ionic, but we still can assign oxidation states as if they were ions in order to figure out the movement of electrons in a reaction that includes this compound. So oxygen would have a -2, making a total charge of -6. So that means each chlorine would have to have an oxidation state of +3 in order to balance it out. So in this case, chlorine is not going to be -1. It's going to be a positive charge. So some halogens can have different oxidation states depending on what it's bound to according to the oxidation rules. Things that can have kind of weird both positive and negative oxidation states do include chlorine. Iodine's another one. Nitrogen is one as well. And there's probably a couple more, but those are the most common ones that have both positive and negative oxidation states. And you guys can practice this. You can assign oxidation states to all of these compounds or polyatomic ions here. And just more practice if you need it. So again, oxidation numbers are indicated by the Roman numerals, and they occur in ionic compounds that have transition metals in them. Okay, so now that we know about oxidation states, we can move on to a redox reaction because we have to have a way to track how the electrons are moving to determine things that are oxidized or they have lost electrons, therefore their oxidation state is going up, or things that are reduced, they have gained electrons and their oxidation state is going down. There's also another term for something that gives electrons to another compound or things that take electrons from another compound. An oxidizing agent, things that are doing the oxidizing, right, are species that removes electrons from another. So they're literally causing the oxidation of something else. Oxidizing agents get reduced because they take away the electrons, they steal them from another compound, and they oxidize them, and they themselves get reduced. So reducing agents are things that give electrons to something else. So they get oxidized and they cause the reduction of other things. And of course, just remember, Leo says grr. So let's look at an example here, another one. This is a single replacement reaction. Those are redox reactions because any reaction that results in a change of oxidation state is also considered a redox reaction. So before we were looking at combustion reactions, those are redox reactions. Single replacement reactions are also redox. So we have magnesium in its standard state would have an oxidation state of 0. In hydrochloric acid, you see that chlorine would have -1 and the hydrogen +1. In magnesium chloride, the magnesium would have a +2, the chloride would have a -1, and hydrogen gas, diatomic in its natural state, would have an oxidation state of 0. So in this case, the hydrogen in the hydrochloric acid is getting reduced, and the magnesium is getting oxidized to magnesium chloride. And the reason is because magnesium is losing electrons. It's basically giving its electrons to this hydrogen in the hydrochloric acid to form magnesium chloride and hydrogen gas. So the oxidizing agent gets reduced. So the thing that gets reduced is hydrogen in the hydrochloric acid. So hydrochloric acid is the oxidizing agent and magnesium is the reducing agent because the magnesium is the thing that's getting oxidized. Um, if you have a reaction that does not result in a change of oxidation states, then it is not a redox reaction. And most of the time, this is going to be double displacement reactions because you literally just have ions in solution that are swapping places. So the oxidation state does not change in double displacement reactions. Then there's also something called a disproportionation reaction. That's what happens whenever you have something that is being both oxidized and reduced. So, for example, chlorine reacting with water to form hydrochloric acid and HOCl. So, this is hypochlorite, hypo, hypochlorous acid. Hypochlorous acid. You can see that chlorine would have an oxidation state of 0 here in its natural state, and over here in hydrochloric acid it would be -1. Okay, but over here HOCl, the oxygen's -2, and then so that means the hydrogen's +1, and then the chlorine also has to be +1. So you have literally chlorine being a -1 here and a +1 here. So this chlorine gas is getting both oxidized and reduced. So when that happens, the same species getting both oxidized and reduced, it is called a disproportionation reaction. And you can look at these other two examples to see why those are disproportionation reactions as well. And you can also do some more practice with this to identify redox reactions or non-redox reactions and identifying the oxidizing and reducing agents and therefore the things that are oxidized and reduced. Okay, so moving on, how do you know if something is preferentially going to be oxidized or something is preferentially going to be reduced? Well, it has to do with the activity series, and this is no longer in your data booklets, but you do have a reduction potential table, which is table 19 of your data booklets, which is basically listing things that are in the order of how willing they are to be oxidized. So you'll see here that things that are at the top of the list, they are more reactive, which means they want to be oxidized more. When we're talking about metals, they want to lose electrons. That is what determines the reactivity of metals, how easily they lose electrons, because metals like to lose electrons to give to other things. So if they're more willing to lose electrons, they're more willing to be oxidized, and the stronger reducing agents they are. So you can see here lithium is at the top of this list. Lithium is more willing to be oxidized than anything below it. And you can see you have a lot of more stable precious metals here because they actually are a lot less willing to be oxidized. And anything that is on the top of the list can oxidize or be oxidized in preference to anything underneath them in this list. And so any single displacement reaction, anything that's on top, can kind of donate electrons to anything below it and become oxidized. Looking at halogens, however, so halogens prefer to gain electrons. They prefer to undergo reduction. So on your reduction potential table, you can see that halogens are mostly on the bottom. They have more positive reduction potentials, which means they really do want to be reduced. Things that are metals that are really reactive and want to be oxidized, they have negative reduction potentials because they do not want to be reduced, they want to be oxidized. So more reactive nonmetals are stronger oxidizing agents, meaning they want to be reduced. So they're going to be at the bottom of that table. So looking at the halogens, the things that are more electronegative are the things that are going to be reduced more easily. So fluorine is a stronger oxidizing agent than chlorine, than bromine, than iodine. So if you're looking at an example where you have chlorine reacting with bromide, chlorine is a stronger is a stronger oxidizing agent, so it's more willing to be reduced than bromide. So because of that, it can actually steal the electrons from bromide to become chloride. Okay, so that is all for this video, and we are going to be moving on to how to write and balance redox reactions in the next one. I hope you guys have a great night, and I will see you in class. Bye!